Swayam Prabha. Digital India. Educated India.
So now, let's give this a name. So hence we get a program, say P, that H computes mod 2 gate. Okay. So now consider the program. Okay. P prime, which is defined as P G P G inverse. Okay. What is this program doing? Okay. So suppose if this mod 2 gate evaluates to 1, then we get in the branching program we get the permutation as H. So here what we get is H G, well, okay, so P inverse is also H for us, okay, and well, P inverse is not defined here. So what I mean is that if I write this as P G inverse, so I will get a H over here as well, and H is its own inverse. So essentially what I get is H G H inverse G inverse, and by lemma 2 what we have is, so this is equal to this is equal to G if mod 2 of x is 1, and if mod 2 of x is 0, then we have identity over here. So identity G inverse will be equal to E if mod 2 of x is equal to 0. So essentially what we are getting is, from P we get another program which is double the length, which is G computing the same gate, and that is what I need over here. Okay. Now why do we go to G from H? What property does the permutation G have? So G is a element of order 3, right? So now once we have P prime, so what we get is, so concatenate all the P primes corresponding to all the mod 2 gates, and we get a program over S3 for the circuit C. Okay. Huh?
The concatenation is giving mod 3.
So the concatenation is giving me mod 3. Okay. So yeah, so one more thing that I should have mentioned here. So this circuit C that we assume, so we also apply lemma 3, okay, before we take this circuit, and we assume that the number of mod 2 gates that evaluate to 1 is either congruent to 0 or 1 mod 3. Okay. That assumes the condition of lemma 3 over here. Okay. So, this circuit C that we have is a circuit that is assuming the condition of lemma 3, that is the number of mod 2 gates that evaluate to 1 is congruent to 0 or 1. Now, we just concatenate all of them. So, what we know is that the number of G's that we have is either congruent to 0 or 1 mod 3. So, therefore, we get the correct output. Okay. So, therefore, the output will be since the number of mod 2 gates that evaluate to 1 is congruent to 0 or 1 mod 3. Therefore, the above program G computes actually what I mean is that the language generated by this circuit C, but it is okay. So, just a little abuse of notation here. Okay. So, this proves the reverse direction. So, now let us look at the other direction. So, any questions? Okay. So, essentially I mean if you think of the proof, it consists of 3 parts. So, first we given a circuit, we assume that this condition of lemma 3 holds. Okay. So, essentially we blow up the size of the circuit and ensure that the number of mod 2 gates that evaluate to 1 is either congruent to 0 or 1. Next, well, for each mod 2 gate, it is very easy to construct a program. So, we use the permutation H to get a program for each mod 2 gate. And the third step is that we kind of show that I mean we show that actually now we can actually from H compute we can actually go to G compute, okay, by applying this result. And now once we go to G compute, now I can very easily show that I mean it directly translates that the concatenation of all those programs will give me a program that G computes the entire circuit. Okay. So, that is the complete idea. So, now the reverse direction. So, the reverse is also quite simple, maybe a little bit more involved, but it is not hard to see. Okay. So, suppose we have a program. Okay. So, let P be a program over S3 and assume without loss of generality that P G computes the language. Okay. So, again we know that if I have a program that is computing it to some other permutation, I can always change it to a desired permutation. Okay. So, assume that it G compute cell. Now,
Is this true for all permutations or permutations of the same cycle type? Like conjugation only always preserves the cycle type. So like if because G is a 3 cycle, like I convert the other 3 cycle to this, but I don't know how to do it for transposition.
yeah. So no, so we can
Only like 3 cycles.
hmm?
Like the definition of the permutation branching is that it always accepts when the
Huh.
last permutation is a 5 cycle or 3 cycle.
It is a cycle, right? Yeah. So that follows from definition. So yeah, so it always accepts some cycle. So therefore, I can convert it to any other cycle. Yeah, true. So now, one more thing that we need to assume is that, so we also assume that every instruction is of the form IGE or IHE, okay, using the fact that G and H generates S3. Okay. So, suppose if I have some other permutation, firstly I can multiply it with the inverse of this permutation, the entire thing I can multiply with the, so let us say I have some sigma tau, okay, I sigma tau. So, first what I can do is that I can multiply it with tau inverse. So, I get sigma tau inverse comma identity. Now, sigma tau inverse can be generated by G and H, okay. So, I can write sigma tau inverse as a product of G and H, and I can just divide it into that many instruction, okay. So, finally what I get is that the entire sequence is basically consisting of instructions of this form. Not only this, what else can we say? Now, if you look at this sequence, so suppose I take an input and I evaluate this instruction on that input. What do I get? I basically get a product of G, H and identities, right. So, on evaluating on any input,
Second permutation is always key.
so I can multiply it with, no, so let us say, so that is what I was saying, that suppose if you have something like I sigma tau, okay, I can write this as I multiply it with tau inverse, right. So, I just add the instruction I mean I just multiply this with I tau inverse tau inverse. So, basically I get something like I sigma tau inverse comma identity, right. Now, this is generated by G and H, okay. So, this is something of the order G to the power A H to the power B, okay, for some A and B. So, now I just divide it into that many G's and H, okay. So, we get a sequence of G H and E, or we get a, not a sequence, let me write this as a product. We get a product of G, H and E's, right. What can we say about this product? How many G, H and E will it have? So, E can be anything, so E's anyway do not matter, but how many G and H's will it have? So, this program G computes L. So, the final output is either G or E, right. So, therefore, how many H's will it have in the product? So, if you evaluate this product, if you evaluate the entire product, all the H's will disappear. Okay. So, what I mean is, actually I did not clarify what I'm asking here. So, we have this as the product. Okay. Now, using the equation that H G equals G square H, we can shift all the H's to the right side of the product. Now, in this shifted product, okay, so where I have a product of G's followed by a product of H, how many H's do I have? An even number of H's, right, because ultimately it is G computing. And how many G's do I have? So, the number of G's is either divisible by 3 or congruent to 1 mod 3, right. Not only that, so now if you look at this equation, there is another important thing about this equation is that it is not actually changing the number of H. Okay. So, let us say if I have a term Hg somewhere, and if I apply this and I get G square H, basically if I am shifting the H, okay. So, the number of H is actually remaining constant. So, in this initial product also the number of H is divisible by 2, it is even. Okay. This equation is only changing the number of G's, but it is not changing the number of H. Okay. So, the number of H's in the product is even. Okay. So, now we are sort of in a position to describe the circuit. What is the circuit corresponding to this product, this program? Okay. So, for an instruction I, G, E, let R be the parity of the number of H's produced before that instruction, then the number of G's that instruction contributes to is something. Okay, so let me just explain what I mean over here. So think of this as follows. Okay, so we have a sequence of instructions and then somewhere I have an instruction IGE. Okay, so I am looking at this program now. I have a sequence IG. Okay, so now before this there were some instructions which were outputting H. Okay, and let R be the parity of the number of H's produced by all those instructions. Okay, how many H's that I am getting. Okay, so if that number is odd, then R is 1, if that number is even, then R is 0. Now why does that matter? The reason that matters is because, so well, if I have H as even, then H to the power an even number will disappear. Okay, so therefore I will only have G over here, and if I have H as odd, then H to the power an odd number is Hg. Then I will have to apply this and kind of shift G to one side and H to the other side, and I will get G square. Okay, so essentially the number of G's that this instruction contributes to depends on the parity of H. If that parity is even, then the number of the number of G's that it contributes to is either 0 or 1, either 0 or 1 depending on whether this instruction evaluates to 0 or 1. If that parity R is odd, then again it evaluates to either 0 or 2 in this case. Okay. So this will be xi into xi plus R. Okay.
For a particular variable.
Huh?
For a particular I this thing.
For a particular instruction. Okay. So for a instruction, for a G, so we can call these instructions as G instructions and H instruction. So for a G instruction, I am just looking at this.
But when we are saying the number of H's, we are shifting to the right side, and this computation we are doing it for, I mean, all the instructions in the program.
Okay, so let me clarify this. So this is a very important point. Actually, this part, okay, so whatever I have said from here till here, we actually don't do it. Okay, so this part is just to analyze the fact that all the H's cancel out in the end.
But how are we combining the H's? Like there are different, if one instruction has I, another instruction has J, another has K. So how are we combining and saying that all H's are different?
So we'll come to that, how we are getting. So we have to build a circuit, right, finally. So I am just going to the point where I will describe that circuit. Okay, this part only analyzes the fact that the number of H's will cancel out in the end. That is clear. What we are given is just a sequence of instructions. Now using this sequence of instructions, I have to build a circuit. Okay, here what I am saying is that if I take one G instruction, then the number of H instructions before that, okay, only the parity of that matters, and that can be denoted by this. So if you look at this term over here, we can actually consider a truth table corresponding to this term. So let me write this. So we have xi, we have R, and we have xi plus 1. So xi is a variable, it can have values 0 or 1. R is a parity, it can also have values 0 or 1. Okay. Now if xi is 0, then anyway this term is 0, right. If xi is 1, then here I have 1 into 1 plus 0 is equal to 1, and if both xi and R are 1, then 1 plus 1 is 2 over here. Okay, and I am doing this computation actually modulo 3. Okay, so I have 2 into 1, I get a 2 over here. Okay, and note that this is exactly what I want. So if the xi equal to 0, what does this mean? So xi equal to 0 means that this instruction evaluates to E. Okay, then, well, what are we saying is that the number of G's that this instruction contributes to. If this is evaluating to E, then this does not contribute to any G, it is contributing to 0 number of G. Now, if this contributes to, if xi is equal to 1, then this instruction evaluates to G, in which case we are looking at the parity of this. If the parity is 0, which means that the number of H's were even before that, then it is only contributing to 1 G, which is exactly what I have. And if the parity is odd, then I am applying this and this is contributing to 2 G's now. That is exactly what I have. Okay. So, this kind of tells me how many G's does this instruction contribute to. Okay. Now, we will write this equation as power of 2 as earlier in that lemma 3, I believe. Okay. So, we can write xi into xi plus r as 2 raised to the power xi minus 1 times 2 raised to the power xi minus 1 plus 2 raised to the power r minus 1. So, this is nothing but 2 raised to the power xi minus 1 into 2 raised to the power xi plus 2 raised to the power r minus 2. We can expand this out and we get a equation, we get powers of 2 essentially, okay, we get 6 powers of 2. So, now we are in a position to build the circuit, okay. So, for a G instruction over here, we essentially will have the following circuit, okay. So, if I expand this out, this will be 2 to the power xi plus, now what is R over here, okay. Output, it is basically the number of H instructions, the parity of the number of H instructions that is evaluating to H, right. So, I can write this as, so I can state this a little differently. So, let y1 up to yk be the inputs to the H instructions before this G instruction, okay. So, again coming back over here, so I have this fixed G instruction, I have some H instructions before this. So, I look at the variable for all those H instructions, okay, and let y1 to yk be the variables corresponding to those H instructions, okay. So, essentially what is R now? Then R is nothing but y1 plus y2 up to yk mod 2, okay. So, whichever variables are 1, I just add them up and it is a parity, okay. So, now it is easy to see my circuit. So, let me expand out this thing now. So, by instead of R, I can replace it with y1 up to yk, and all these powers are modulo 2. So, that is not a problem for us. So, we can write xi into xi plus r as 2 raised to the power xi, or okay 2 xi plus 2 raised to the power xi plus y1 up to yk minus 2 raised to the power xi plus 1 minus 2 raised to the power xi plus, sorry, minus 2 raised to the power y1 up to yk plus 2. Okay. So, 2 raised to the power 2 xi is anyway 0, because I am taking all the exponents modulo 2. So, 2 times xi is 0. So, this is anyway 0. So, this cancels off. So, this can be made as plus 2. So, we can change minus 1 to plus 2. So, minus 2 will be plus 1. Yeah, we can do that. Yeah, that will evaluate to the same thing, right? So yeah, exactly. So that is another way of, correct. So different color. So that's a good point. So we can change this to plus 2 and we change this to plus 1. So essentially then what we get is two to the power xi plus y1 up to yk plus 2 to the power xi plus 2 to the power xi plus 1 plus 2 to the power y1 up to yk plus 1 plus 2. Yeah. So now we have all pluses, so we can build the circuit appropriately. Okay. So we have a mod. So we have the mod 3 gate, and 1G instruction would now correspond to 5 mod 2 gates. Okay. And this is for 1G instruction, and we do this for all the G instructions now. Okay. So this completes the proof for us. Okay. Okay, so any questions? Okay, so I will stop here then.